I'm very excited to be here today to get to share with you and re-explore this part of deep learning and machine learning. And I wanted to use this title of imagining and reasoning to sort of excite you and maybe to stimulate your creative juices about what the future of deep learning can be. And so maybe to start with, I would like you to all think about the reasons that excited you to be part of machine learning and deep learning. What is the reason that brought you here today, the ultimate goals that you want to achieve through machine learning? And I think having met a number of you, for many, some of you want to understand the statistical and mathematical foundations of learning systems and what it means to learn from data. For others, you are part of a new era of scientific discovery where we have very large scientific experiments, and as a result, we need even larger machine learning, even more impressive machine learning to really understand the nature of the world. Some of you are innovators and technologists and entrepreneurs of tomorrow, and you want to disrupt and create new markets, and some of you are on a quest to solve intelligence. And I'd like you now to think about what the components you think are needed that will form your ideal machine learning system.
Shakir, thanks for thinking about me.
Obviously, you were definitely in mind. So what are the components of your ideal machine learning system, the components that will help you reach your ambition? And I think throughout this week, definitely part of the solution involves the powerful supervised deep learning systems that you've learned earlier in the week, which are now state-of-the-art in machine translation, object recognition, speech to text. They involve the things you learned about yesterday, which involve reinforcement learning, learning from rewards, and, but there are some other things which haven't been. How can we learn systems that move beyond associating inputs to outputs or associating actions to rewards? How can we build systems that really understand the world, that can synthesize different sources of information, fuse them together to really unpack how the world will evolve? Can we build a system that understands that there are objects in the world, that there are factors of variation underlying these objects, and they can be used to be manipulated and reasoned against? Can we establish concepts that are in the world and use these concepts for high-level reasoning and decision-making? Can we build ways that let our models know that something is new or surprising? And ultimately, can we build systems that help us imagine and generate rich plans for the future? And these are the places of generative models that I want to share with you today. But when we look at all the things you've learned about this week, supervised learning, recurrent networks, reasoning and attention, and generative models, these will be part of the suite of what we'll call complementary learning systems. Systems that work together to really help us achieve whatever your ambition for machine learning was. So just some keynotes. When I write a function f, the function f is always going to be a deep network of some form. I won't go into too much detail about its exact form, but that's what the function f is going to be. And you've seen all the topics that I'm going to speak about today. So what I wanted to do was leave you with some principles, some tools, and some tricks that you can use, not just for generative models, but throughout machine learning, and give you a sort of different perspective. So some of the themes that I wanted to leave with you are the design of probabilistic models, Bayesian deep learning, stochastic optimization, methods for reasoning and control. And in some way, everything I'm going to talk about is about the problem of density estimation. So whatever you know about the problem of statistical density estimation, bring that to the front of your mind, and then we'll use that to go forward. So I have sort of 6 parts. We might not go through all 6 parts, but the first part will be a bird's eye view of generative models. What is the current state of the art of generative models? Then I love dealing with models, and there is a model for every occasion. For whatever kind of system you want, there is a model that we can build, and we're going to explore all the different classes of models that we have. Once you have a model and you have data, the way you integrate data into your model is through a principle of learning and inference. And there are 2 principles that I wanted to discuss. One will be about evidence estimation, and the other one is going to be about 2-sample testing. And then we're going to take our models, we're going to take our inference, we're going to combine them to build different kinds of algorithms, which there are many ways to do that. And then we're going to use a case study of variational autoencoders to explore all the different ways you might want to build models. And then we'll try and summarize and look at things. So, okay, there is a huge diversity of generative models, and I want to take you through all of them. So the simplest application is this one. It's data imputation. If you really understand the data of your world, then you will be able to understand its underlying statistics. And the classical problem is missing data imputation or removing noise, because data in the real world is not clean. And so this is an example from a model called Pixel RNN, which if you need to complete or fill in the missing half, these are the kind of completions it can do. And you can see that good models allow you to explore the variation in the world that is actually plausible. And this kind of variation is actually what you need for powerful reasoning and probabilistic systems. But this might be the simplest one, and I'm going to go from simpler applications to more complicated ones. The next type of thing is semi-supervised classification. Generative models have a very important role to act in the service of supervised learning models, ways to actually make them more data efficient or to be more act as better regularizers. And so in the semi-supervised learning problem, you have very few labeled data points and a lot of unlabeled data points, and how can you do this transfer of knowledge from the labeled data point to the unlabeled data points? And the generative approach is right now one of the state-of-the-art methods for semi-supervised classification. Then we have generative models are closely related to the problem of compression and communication. And I'd like you to imagine we all have phones, we all deal with videos and large images, which we need to communicate over long distances. Generative models have the role for us to communicate and compress those data very efficiently and then send them, and we can even control to what extent we want to have this kind of compression. So that's another useful application. If we really want to understand scenes in the world, then one way of dealing with this is to understand its 3D structure, understand that there are certain physical constraints, some intuitive physical notions of the world. And so this bottom video is the classic example of the Necker cube, where there are certain ambiguities in how you can perceive and view this kind of cube. And then there's a completion process where you have to take the left half and you have to see how it fits. And it does very much what a human does. It forms the rest of the cube and then realigns it to fit with the rest of the cube. But we can also move to other things of more complex three-dimensional scenes. Think of a generative virtual reality where you can build and generate these kind of scenes and really interact with the world. So an important other aspect that generative models have is in the problem of rapid scene understanding. So here is a scene of a camera looking over a set. And when you do reasoning in the scene, you want to very quickly know how many objects are in the scene, what kind of objects are in the scene, and the kind of factors of variation associated with those objects. And so you can see the reconstruction here is the red pot and the camera, which shows that it's in the right position. It knows how many scenes there are, how many objects there are. And this bottom video is of the learning process of such a model that is both trying to simultaneously learn the identity of digits, it's also trying to learn where these digits are, and it's also counting the number of digits and letting you know that in this case there are 3 digits in all of these images. So this kind of scene understanding will be very important. Like humans do, we want to have machines that when they see new data one time or very few times, they can explore the data, understand their variations, and use prior knowledge to really do that. And so in this task, we are looking to explore the different ways, generate alternative examples of the images at the top row, which the model has never seen before, a task that we call one-shot generalization. So you saw a bit of this question yesterday, that we can now use a generative model to actually build simulators of an environment. And if we have a simulator of an environment, then we can do very long-term rollouts. We can make predictions about what will happen. We can do counterfactual reasoning in some way. And then we can actually account for this when we do our decision-making as we go forward. Another kind of thing, so this is a video of a 3-dimensional labyrinth. And if you and I operate in environments like this all the time. So what you need to do for control is form the state representation that was called yesterday. How can you form a representation of these states and use these states to actually do control? There's actually a control system happening here that uses a generative model to form the state representation, and based on this state representation, then actually does the control, and the task is actually to find the green apple, which gives you a reward. So this kind of representation, though, we want it to actually be a little bit more structured. And so can we actually say that there are concepts within our representations that factor in interesting ways? And so in this video, this is of the Atari game called Sequest. We explore a few different, you can see that generative models help you unpack different concepts. There's the concept of the oxygen bar, which is being filled out. There's the concept of the submarine moving up and down, a concept of the submarine moving left to right, a concept of lives which matter in this kind of game. And the ability to detect these kind of meaningful representations that allow us to do reasoning at a concept level will be very important. So yesterday, Joël mentioned the topic of exploration. And in the typical, everything that was mentioned about exploration in this game in Atari called Montezuma's Revenge, we usually can only explore 2 rooms. This is actually the structure of the game. There are 26 rooms. And usually you can only see these 2. But using a generative model, you can actually see and learn what is new and what is interesting in the world. You can equip your agents with that knowledge, and using that, using that information, you can then build a system like this that now lets us explore 15 rooms in the world. And so now Montezuma's Revenge is getting much better through the power of equipping generative models within the reinforcement learning setting, right? And finally, there's, yes?
But you need a policy to be able to do that exploration, right?
Yes, the policy comes through Q-learning in this case. And finally, there's the problem of how can we do temporal abstractions and make plans into the future. And you can think of generative models that actually have a role to play in helping you generate plans into the future. So this is a model of Miss Pac-Man, and on the y-axis is the number of actions. There are a discrete number of actions. And on this x-axis, there is time. The white line sort of indicates where we are in the current point in time. And this generative model actually generates plans into the future. You can see beyond the white line, there's a bit of a plan that is already formed. And then it has a way of switching between plans on the fly. So this is sort of the state of the art of generative models. We have models that allow you to do simple tasks from missing data, which helps you understand the structure of your data, to do semi-supervised classification, density-based exploration, representation learning, and concept learning, one-shot generalization, simulating environments, compression, macro actions, and planning. And I think there are many, many other applications which are not listed here. But these are some of the ones that I think we've seen a lot of progress in recent time. So just to really emphasize the kind of progress that we've had in the last few years that Russ mentioned earlier, this is on the MNIST benchmark using the log likelihood measure. And we would start off with simple models like mixtures of Bernoullis with 500 clusters, which weren't that good. But over time, we've done much, much better models. And under any measure, we are just getting better, and under any different kind of model. And today, we have really good models that actually do really impress people. They inspire people. You really think. And then under a different generative model, different data set, we have the same kind of, this is the omniglot data set. And so we're really making progress. Of course, not every model can be measured against this log likelihood metric. So if you want to look at the actual kind of generations that they can do, again, the same thing, we really are making a lot of progress from simple things like VAE that weren't very good 3 years ago when we created them, to now many new models which actually represent the statistics in images, have the good kind of structure, sharpness. So that paints the picture. So for the rest of the talk, I'm going to describe to you the way I understand and use machine learning. So there are 3 parts of my machine learning framework. It always starts off with a model. The model will embody everything you know about your system and that you want to work with. Once you have a model, you will choose a system of learning principles. And your learning principles will then get used to help you deal with your data. And for any combination of learning principle and model, you can form very different algorithms. And so we're going to do 3 parts to explore different kinds of these. So under models, we're going to consider 3 different types of models. The first one will be fully observed models. And you saw many of these models when you looked at RNNs earlier in the week. Then we're going to look at transformation models. You've all used these if you've generated random numbers already, but they are a very important class. And then the third class of models we'll look at are latent variable models that help you establish hidden causes and the structure of your data generating process. Then there's a huge smorgasbord of learning principles which you get to choose from, and different models make different principles more applicable. And you've used maximum likelihood and map estimation this week. You've seen lots of variational methods, and I'm going to try and put them together in a different way. And then once you have a model and inference, you can combine them in many different ways. For example, that you just saw with the restricted Boltzmann machine and maximum likelihood, there are many different algorithms to combine those 2: contrastive divergence, parallel tempering, natural gradients, etc. So, OK, that's sort of just the first part. And I think we'll just dive straight into different kinds of models. So There are three types of generative models that I mentioned: fully observed models, transformation models, and latent variable models. And you really need to think about what the problem is that you are dealing with, and depending on the problem, you will have to choose one of these kind of models. And there are many design dimensions that you actually will deal with. You have certain data types. What kind of data? Do you have binary data, real valued, nominal? Are they strings? Are they images? Are they graphs? There'll be certain dependency structures which you might want to model, whether they are independent, whether they are sequential, whether they are temporal, spatial-temporal, etc. There'll be different representations you might want to have. Do you want to have discrete or continuous or some kind of mixed representations? Is there certain dimensionality that you want to consider? Do you want to have parametric or non-parametric modeling? And then there are other aspects of computational complexity, modeling capacity, bias, uncertainty, calibration of your data sets, interpretability. All these are things you sort of have to think about, and different models will trade these off in different ways. So the first class of models are called fully observed models. And what defines a fully observed model is that they are models that use the data directly, and they do not introduce other unobserved and random local variables. So parameters in a model are global variables because they are properties of the data set in total. But a local variable is something which is particular to an individual data point. And so fully observed models do not introduce other variables that are particular to data points. Right? And they need to be stochastic, otherwise, so that's the definition. So you've seen Markov models earlier in the week. This sort of generalizes the entire class. And the generative process is very simple here. You generate the first dimension of your data from some distribution, a categorical in this case, given some parameters pi. You generate the second dimension given the first one, and so on. You generate the ith dimension given all the other ones before. So this is the image of generating pixel I in this image given everything in the blue case. And then that is the probability models. And when I write this function f, you can put any kind of deep neural network within this case. They can be fully connected, recurrent, etc. So then there are many properties of these kind of fully observed models. And some of these properties include that you can directly encode the structure of the data that you have, which can be very powerful if you have certain knowledge. If you are modeling astronomical phenomena, then you have this kind of knowledge. Any data type can be used, which is very flexible and powerful. And for directed graphical models, the parameter learning is extremely simple in these models because the log likelihood is immediately available, and you do not need to introduce other approximations. And it's very easy to scale these kind of models up to very large systems over multiple GPUs, very large data sets, and we have many good tools for optimization now for this. In the undirected, the negative is that they have this ordering sensitivity which comes into play. In the undirected case, though, the parameter learning can be difficult. Yes?
There's also a disadvantage sometimes, like in pixel RNN, which is that computation becomes very sequential. And on GPUs, for example, that's not very convenient.
Yes.
And efficient.
Yeah. So there's this, the last point I'll make, which is about the slowness. So for undirected models, just to complete that, the parameter learning can be difficult. The problem of the normalizing constant that we just saw in the earlier session. And for all these models, this generation can be slow. You have to iterate sequentially through the elements, use a Markov chain, and it's not efficient of your computing resources. So, depending on what your problem is, you have to consider these kind of things. These are some of the generations you can get from a pixel CNN model, conditional on labels. So I wanted to explore the different classes of models on two dimensions. One dimension is directed and undirected, and the other dimension is discrete and continuous. And for any combination of these, you'll probably find a model. And this morning we saw about log linear models and Gaussian MRFs. The models I just mentioned are nonlinear autoregressive models and real-valued NAID. Many people are working in this block of discrete and directed, NAID, fully visible sigmoid belief networks, pixel RNN, and there are other models as well. So transformation models take a very different approach. They say that you have an underlying source of noise, and this source of noise is going to be transformed through some parametric function. So this model basically describes everything. And the image I sort of want you to keep in your mind is of a sort of a system of pipes. And the pipes represent this function. And what you can do with this function is you can adjust some properties of these pipes, the thickness and their length. And what you put into these pipes is some source of noise, and what comes out of the pipes at the end is going to be some new distribution. And if the function represented by these pipes is invertible, then you can just apply the rule for change of variables, and you'll be able to actually know the distribution at the end. But you don't necessarily need to know this. We have the ability to create very arbitrary functions. And so one example of these kind of models would be what they call generator networks. And it's very simple degenerative procedure. You have some source of noise, a Gaussian, for example. Then you push this through some nonlinear function. And out at the end, you get our samples from a new distribution. And this transformation can, again, be any kind of function. So these kind of models have a very different kind of set of properties. The sampling is very easy. As you saw, I just needed to take some random source of numbers, and I get them out at the end. It's very easy to compute expectations in these models. There's a property that we call the law of the unconscious statistician that uses this, that if you want to compute expectations with respect to the final distribution, you just need samples. And again, because these models are going to allow us to use classifiers and other very large-scale systems, they can be scaled up to very large scale. But there are certain constraints which these models impose on us, which can be difficult to satisfy. It is very difficult to learn invertible neural networks, or the optimization can be very challenging. And then there's an issue that, unlike the fully observed models, there is no noise model at the end, which may be an issue. So not having a noise model on the final output means that it's very difficult to extend to generic data types. If you wanted to generate binary data, this will be very difficult to do. Data in the real world is not. So if you needed to account for noise in the data, then this is a bit hard to do. And since you do not have access to the final distribution, computing the marginalized likelihood, which lets you do model comparison, scoring, can be very hard to do. Yes.
In GAN, it's very easy to add noise in the visible if you want, but we don't do it because we don't want it, because the real images don't have that kind of noise.
Yeah, in fact, we have done it.
But then it becomes a VAE. Right. Latent variable models with noise models are directed models.
The noise, we chose to put it at the top, but you could easily put it anywhere you want. There's nothing in the algorithm that prevents you from doing that. But
we've also done experiments where you put it in the top and the bottom, and what happens is it just learns to put the variance at the visible layer.
At the visible layer?
Okay. It doesn't reflect the data distribution.
Yeah. So again, this is a good point. You need to know sort of what you actually want to do, and depending on what you want to do, the kind of model you use will actually affect your choice. So this is from the conditional generative adversarial model.
A geometric way of understanding this, the way I understand it is, images, sounds, and things like that, they live on a low-dimensional manifold, or very near low-dimensional manifold. As soon as you add isotropic noise, like Gaussian noise, you get something that's not going to be on that manifold. Right?
Yes.
And so you should not have noise at the visible. And for me, it's a defect of things like Boltzmann machines, VAEs, and things like that. Like you have to add noise in order to get a meaningful model.
But Yoshua, if you don't have that and your model generates pixel, which is not just like white, you put zero probability on it, and which can.
But maybe likelihood is not the right objective here.
I don't know, I think this is a very good point that we actually need to debate. The fact that some points can have zero likelihood is a questionable statement, right? It can be dangerous. Again, you need to think about what you're doing. I like these class of models. As I said, we've all used them before. So there's two ways to really think about these. You can think about them in discrete time, or you can think about them in continuous time. If you have generated random numbers before, then those kind of models usually take a uniform random number and then give you a sample from a Gaussian. Those are called one-liners. And then you have the generator networks from GANs, and then you have other volume and non-volume preserving transformations. And in continuous time, this rule for change of law of variables is called the Fokker-Planck equation or Kolmogorov's equation, and then you get the equivalent in the continuous time domain. So there's a lot of good models to explore in this range. And then you have the last case, which is sort of, yes?
Quick question about the previous slide, please.
Just one more before?
No, this is the right one. How are the GANs related to diffusion models?
So the kind of a diffusion that you have to think is that the diffusion gives you a mechanism to do a flow of the probability. So the GAN defines this flow, a way of reshaping the probability to give you the thing at the end. And so these are all what diffusion models do. Diffusions take an initial source of randomness, shape them over some path, and then out at the end you get. Obviously, diffusions will add extra noise at different points in time, but the thinking is at least conceptually the same. So latent variable models are going to actually specify a set of underlying causes that you think represent how your data is generated. So this is an example of what's called a deep latent Gaussian model, and the generative process is, again, very simple. You start at the very top, generate some Gaussian noise, come down, generate some new random variables, condition on the previous one, generate some new ones, condition on the one before, and eventually generate some data from a noise source, which is what is not in maybe some of the other models. And you can have lots of other kind of skip connections in various ways, and all these functions, mu and sigma, are also deep networks, right? So this is what Russ mentioned by having these deterministic layers in between these stochastic layers. And so these ones also have a different set of properties. Again, like all the others, the sampling is very easy. It's a very easy way of including hierarchy and depth. And it's very natural to want to encode the structure you think underlying your model in this way. And the issue of the order dependency, which came up maybe in the fully observed models, is removed here, because integrating out latent variables induces dependencies, which means you do not need to think about this. Right? Latent variables provide some compression and representation of the data, and again you have access to the likelihood, which means that you can do scoring, model comparison, and model selection. Right? But when you have unobserved random variables in a model, then you have to compute the probability of that random variable given data. And this task can be very difficult to do in general. The marginalized probability is itself not easy to compute, and you might need to have some clever kind of approximations. And the kind of approximations themselves need a lot of creativity. The kind of posterior distributions need to be approximated. So, but this is probably the largest class of models that's been explored, more than 150 years of research, starting with Spearman when he created PCA. And you can think of useful and interesting dimensions for me are the parametric and non-parametric distinction, deep versus linear or just more direct non-deep models, and discrete and continuous. Most of us are sort of working around here, where continuous, deep, and parametric models, where you have things like VAEs and draw. But then you have other interesting models in various other cases, like non-parametric, deep, and discrete. Hierarchical Dirichlet process. All of these. The point is just to show that these are all the same class of model, and the reasoning system you use for one can be used for the other. So there's a lot of different models to explore, and wherever you find your interest, you can find a model that helps you fill that category. Okay, so that's everything about models. If there are any questions about modeling, yes?
You mentioned briefly that invertible neural networks are hard to train. Can you elaborate on that?
So typically what you have to do, there's a lot of work on invertible neural networks from the 90s. Maybe you know more of this from me. So what you have to do then is there are a set of constraints and the parameters that you have to make them. So even in simple univariate functions, this is difficult to do. And the optimization can be very hard. You have to add extra constraints to make sure the gradients behave well. We've tried it in some previous work, and it's not great to do. So yes?
Can you just go back a slide?
Yes?
The composited engine that they put?
Yes.
What is that?
It's sort of, an IBP builds a non-parametric private discrete random variables, and it is the typical formulation is direct, that you just have this one layer of parametric prior, then that gives you the data. But you can have multiple layers of stacking this non-parametric discrete prior. Think of a sigmoid belief network, but the non-parametric equivalent. Maybe I have the wrong name, but there definitely exists. I'm going to add all the references in the back for all of these models and things. Okay, any other modeling questions? No? Okay, so once you have a model, the process of combining data into your model is the process of learning and inference. And I want to explore two principles of inference with you. So common inferential problems that you'll find in machine learning and statistics include evidence estimation. Once you have data, you want to know what is the probability of your data. And once you know this probability, you can do a lot of things. Then there's sort of moment computation. There are sort of statistical quantities that you want to do for summarization, and then you want to sort of compute these moments in different ways. Prediction is the common one that everyone wants to do. Given some old data up to xt, you want to make a prediction of xt plus 1, or they can be entire data sets. And sometimes you want to do testing as another inferential problem. You want to be able to look at two hypotheses and say which one should you actually use in the case of model selection, for example. So the first kind of principle for inference that I wanted to go about is on the model evidence. So the model evidence is the way of computing the probability of the data that you have. And we're going to look at the model evidence in the class of latent variable models. And you've seen much of this already, so maybe we can go through a bit faster. And the model evidence is what you will use to score your model, to do model comparison, to do model selection, to do moment estimation, to do normalization, to do posterior computation and prediction. Once you have this single quantity, you basically know as much as you need to know about your data to do anything you want to do. So the principle involves taking steps to improve the model evidence given the data that you have. So the principle is very simple. Given data, integrate out anything that is unobserved and use the value of x. Now, this integral in general is not known to you, but the main principle is to transform this integral into an expectation over something simpler. And well, you've seen that trick yesterday and even this morning, so I'm going to start with importance sampling, and we're going to just do a little derivation. So this is the integral problem that is common to almost every inferential problem that you have. Can we integrate out latent variable z? But we don't know how to do this. What I'll do is introduce the proposal distribution, which will be called Q. And I'm just introduced a 1, so it's just multiplied by 1. Then I re-weight this thing to introduce the importance weight that you saw earlier mentioned. And now this itself is an expectation of a different quantity, is an expectation under the distribution Q. So I can form this importance weight, which is W. I can easily sample from Q. And then the principle of importance sampling is to evaluate this integral by Monte Carlo integration, which means just averaging the importance weights given these samples. So just a little bit of notation for the rest. Everywhere I'm going to write Q of z, but I actually mean Q of z given x, but I'm just going to leave out the x for convenience. And there are some conditions for importance sampling. So importance sampling is the simplest way and the most fundamental way of computing integrals. We use them everywhere. You can do a slightly different trick at the end. So here's our integral problem again, which we need to compute. We introduce the proposal. We rematch the terms to introduce the importance weight. And now instead of applying Monte Carlo integration, I'm going to apply Jensen's inequality that you saw this morning that says that the log of an expectation is greater than the expectation of the log. And now this gives a new quantity, which I can rewrite this way, which is an expectation of Q of z under this log likelihood term and an expectation of Q of z under this log ratio term. And this is the famous variational lower bound that we describe everywhere and that you've seen throughout the week. Yes? No? OK. OK, so if we're good, you've seen the derivation a few times. So I wanted to just unpack. This quantity is called the variational free energy. And it has a number of useful quantities. There's this distribution Q of z, which will be the approximate posterior distribution. This Q of z represents your current understanding of the posterior distribution of the latent variables given the data. Right. And there is this other term, which is the reconstruction term. Log likelihood terms are reconstruction terms, so this helps you measure how well you are matching the data that you have. And then there is this penalty term, which naturally arises. You do not have to design it. It is derived for you, and it is the way of introducing Occam's razor into your problem and dealing with model complexity and penalization. So this one here has been very familiar to you this week, but there are other kinds of variational bounds. The one you just saw from Russ this morning was the multi-sample variational objective, or the importance weighted objective. You can see the top one is a special case of this. Then you get sort of Renyi variational objectives, which is a generalization of the previous two. And then you have other kinds of variational families as well. But the point of these kind of variational families is that the solution for all of them, the solution Q of z, is the same for all of them, which means find the Q of z which is as close as possible to the true P of z given x. So you can choose any of these kind of bounds that you like. The solution in the end is the same. Some of them make optimization easier than others, or let you unify different ways of thinking. So, OK. Are there any questions on sort of variational inference and this sort of part of the talk? OK. So the second principle for inference that I wanted to look at is on two-sample testing. So for many models, you do not have access. You only have access to an unnormalized probability, or you have just partial knowledge of the distribution. You really don't know anything. You know the noise source at the beginning, and you know the function, but not much else. So a different way to do this is then just to compare two distributions. And so the principle of learning here is that we want to compare a distribution of training data with a distribution of some other data source. It can be a test data set. It can be a data set that we generated from our model. It can be anything. Right? So the principle of two-sample testing will be to say that I want the probability of my training data set to be the same as my distribution under the data set I generated, for example. So you want these two probabilities to be 1, or you want them to be the same. Right? And The reason you want to do this is because you might not be interested in computing the marginal probability. And if you aren't interested in computing the marginal probability, then this problem here of computing a density ratio is a far easier problem, right? And so the trick of density ratio estimation is going to be to transform the problem of density ratio estimation into the problem of class probability estimation. And that is something we know very well how to do. So, okay, a little bit of notation just to set up. I have two data sets, x hat and x tilde, which I'm going to combine together into some new data set, which I'm just going to call x. I'm going to use the random variable x to denote that combined data set. I'm going to assign some labels also to this data set. So I'm going to introduce +1 to everything from the data set that was x hat, and -1 to everything from the data set that was x tilde. And then there is this equivalence that the probability of x tilde is just the probability of the combined data set conditioned on the label 1. And similarly for x tilde, it is the probability of the total data set conditioned on the fact that you have the label -1. Right? So this is just the setup of our problem. I'm going to write two things. I'm going to remind you of our problem, which is the problem of density ratio estimation. And the second problem, which is just going to be Bayes' rule, which you need for everything. So let's start. The conditional problem that we started with is to compute this conditional density ratio, which you can write, because of this equivalence that we have, as the ratio of two conditional probabilities, P of x given y equals class 1, and P of x divided by P of x given y equals class -1. Now, using Bayes' rule, I can replace the terms of these conditional distributions. So I do a Bayes substitution, and now I'm going to get these two terms here. And now I want to do a bit of a cancellation. So P of x is the same on both sides, so I'm just going to remove those two terms. Now, I'm going to assume that the data set that you have from x tilde and the data set that you have from x hat are equally balanced. But if they are not equally balanced, you can address that imbalance by these two probabilities at the bottom, P of y equals +1 and P of y equals -1. But let's assume it's equal, so they also cancel. And then basically what is left is this quantity. It says that the density ratio we are actually interested in is actually equal to the ratio of the two class conditional probabilities, right? And so that is the main point I want to leave with you. The problem of computing density ratio estimation is equal to the problem of class probability estimation. And now, what is the point of all of this? So basically, let's try and learn this classifier at the top. So there's a scoring function. Now I need to learn a probability, P of y equals 1 given x. So I'm going to create a scoring function d, which is theta of x. Then obviously 1 minus that quantity is the class of the negative term. Because I'm doing binary classification, the Bernoulli outcome is going to tell me that the log likelihood is going to be log of d of the x hat data set minus log 1 minus d of the other data set, right? And so I'm going to develop basically a two-sample criterion, which is going to tell you, you can optimize this loss function where x hat is one data set and x tilde is another data set. These two can be any different data. One can be a training data set, and the other one can be a data set which you generated from your model. And so now, how can we use this kind of criterion in different ways? So typically when we do generative, I've assumed up to this point that xgen and xobs are fixed data sets. But when we do learning, xgen is not fixed. It is also something that we are learning on the fly. So in the case of transformation models, for example, where you have z passed through some function and you get xz, we can replace xgen in this two-sample criterion with this function f directly, right? So now the two-sample criterion leads us to what ended up in the adversarial networks, which is that you get this loss function which tells you to take the expectation of the log of your scoring function under observed data and under the other data. Yes?
So the second equation is missing some indicator functions to say that we're talking about coming from one class or the other class, right?
Well, this equation here?
The second. Yeah.
Yes, I've written here x hat and x tilde, which already is the indicator is implied in there. If I had written it up in the previous notation of x given y1, then there'd be a d in front and a 1 minus d in the front. But yes, it's just to simplify, I wrote x and x tilde directly, so you'd see the connection. Okay, so now this loss function is a very different beast from the variational loss function you saw before. The variational loss function was a lower bound, which means that any optimization you do on that bound always is guaranteed to improve the bound. So it gives you a tool for debugging. This kind of loss function is sort of playing a game with itself. a classifier always wants to find a clear decision boundary to tell you what is generated and what is not. But we actually do not want the classifier to work this way. We want our classifier to have probability 0.5 for generated and true data points. So then basically we attain this alternating optimization principle where we maximize the classifier's parameters theta and we minimize the classifier parameters phi. Right? But this is just in the case of these transformation models. If you are working in other classes of models like undirected models or directed models, this same two-sample criterion will be called noise contrastive estimation. Of course, if you are doing in more statistical theory, then two-sample ratio, density ratio estimation was something you do a lot of the time. Importance estimation that you see in reinforcement learning comes up all the time, and you can use this as a solution to that problem as well. Okay, so are there any questions on maybe two-sample testing, evidence estimation, or learning algorithms in general? Okay, so let's go on. So now that we have models and we have inference methods, we're going to put them together, and we can build different kinds of algorithms. And I want to look at about 3 different principles for building algorithms. There'll be stochastic approximation, amortized inference, and stochastic optimization. You've seen all of these already. Yes?
You could also fit like CD training of RBMs into that.
Yes, I think you could. But, well, yes, you can, because they do it in the noise contrastive estimation. That is exactly what you do for log linear models. So don't know if it works that well. Right. It's, yeah. It's not bad. It's actually as good as doing anything else. But typically people do it in the language modeling case, which is a good use case for that. Okay. So the classic thing that you learned in the textbooks of machine learning was about the EM algorithm. And the EM algorithm will be the basis of everything. If you know this, you'll know almost everything in machine learning. So yes?
I think you should remind people of EM. Because
I'm going to do exactly that. So the EM algorithm basically operates this way. You have a loss function as follows. And the EM algorithm is just an alternating optimization between 2 sets of parameters. Right? So the variational EM is actually a superset of the standard EM algorithm. So I just need to talk to you about only variational EM, and you'll understand EM. So the alternating optimization of model parameters and distribution parameters, or variational parameters, right? So an EM algorithm always works as follows. You write a for loop, and then you repeat. E-step computation, compute the gradients of the function with respect to the variational parameters phi. Then you go to an M step, you compute the gradient with respect to the model parameters theta, and then you do this in a loop and you iterate. And then because the EM algorithm is always optimizing a bound, every step improves this free energy up until you can't learn any more from the data. So let me go and unpack this EM algorithm in a little bit more detail. So again, the EM algorithm always says repeat the following steps. And then you do your E step. You say for I equals 1 to n. If you've written an EM algorithm, you can remember writing this in your code. Then you do the gradient update step for the variational parameters phi, which is compute the gradient of this quantity f with respect to phi. Phi lives in the term q. Then you do that for all the data sets. And once you are done, you store all the phi's in a table. Then an M step update, which says compute the theta using all the phi's. This expectation of a phi requires you to have all that knowledge. So the key point that I wanted to bring out here is that here you do a sum for all the data in your data set. And here there's another sum for all the data in the data set. So in the 90s, we could do, because n was 100 or n was 1,000. But in 2016, n is 10 million. This sum is not possible. But this is the exact gradient. So instead, what you can do is replace n with something smaller, a mini batch of data instead. So this is called the stochastic approximation technique. And because you resample n data points from the full data set, this introduces noise, which is why it's called a stochastic approximation. And this has various names: online EM, stochastic approximation EM, stochastic variational inference. And it is the main tool that you use for stochastic gradient descent. Right? And you'll do this now. Basically, this is doing stochastic gradient descent for these 2 terms. So there's one other sort of problem with this setup in the E step. So if you look here at the E step, this E step is what I typically call a memory list step. So for every data point I equals 1 to n, you compute 5n by some optimization, and you store that 5n in a table. When you compute phi of 1, you compute that optimization. Computing phi 2 does not use any knowledge of phi 1, the fact that you've computed this before. You redo it again, and you do this for all the data points. So every phi that you compute uses no knowledge of the fact that you've already computed some phi's before. So what you can do is now replace this entire E step by using a model instead. So this is the principle of amortizing some computation into a model. And so this is how the principle of an inference network can get introduced into a probabilistic modeling scenario. Right? So you introduce a Q network, which is now an encoder, which will basically summarize all the data points and will allow you to reuse and transfer the fact that you've done E-step computations between them. This inference network introduces a set of global parameters into the model that's used for test and train. And I call this amortizing because there's this dark knowledge, if you remember this dark knowledge notation, that gets entered into this network that helps you spread the cost of learning E-step, learning phi's for every data point. Right? You can now do a joint optimization, which is very nice. And so the point is that inference networks provide you an efficient mechanism for posterior inference with memory in these kind of latent variable models, for example, or any kind of Bayes net. So okay, amortized variational inference then basically takes the idea of using these kind of inference networks within the variational inference setup. So just to remind you again of this free energy bound, we have expectation of Q of Z, which is the approximate posterior. We have our reconstruction term and our penalty term. Then basically, by introducing an encoder network, we form a stochastic encoder-decoder network. So basically, any stochastic encoder-decoder system will effectively implement variational inference. And so basically, what you have the model, you can now call a decoder, which is your likelihood function. Your inference network is an encoder, which takes data X and gives you Z. And basically, you can also see this as a way of transforming an autoencoder into a generative model. Right? So when we have a specific combination of variational inference in latent variable models using inference networks, this specific combination of these three things gives you an algorithm that we refer to as a variational autoencoder. But always remember what the model is that you are using and what kind of inference. For any model, you can replace it with a different inference, and you get a different kind of algorithm. So I wanted to just connect this to the problem of compression since we've established these encoder-decoder systems. So in minimum description length compression, you basically have exactly the same loss function where Q of Z will be a stochastic encoder. Then you have a term which represents the data code length, which is what you want to measure. And then you have a hypothesis code, which is what you want to produce. And again, this is a different kind of stochastic encoder-decoder system. And the principle of minimum description length asks you or requires you to accept that because there's regularity in the data, the latent variables can be used to compress this data. And so the minimum description length asks you to find the shortest message for your given data, and the shortest message is this marginal likelihood bound. So there's the encoder-decoder system, and the approximation to the ideal message, which you can't compute, is this variational bound. I also wanted to connect to other kinds of models that you might be using. So message passing is another very important inferential approach, which is very different from the approach that I just described. And typically, you'll have a factor graph of this kind. And the factor graph has certain factors, and there are assumptions, usually a factorized assumption on these graphs. And the memoryless inference approach is just to basically do exactly what we're doing in the E step of the EM algorithm, which means compute this argmin, which in the case of cavity methods involves computing the projection and the re-optimization of the distribution. The amortized inference is very simple. Replace that computation with a neural network, and then things will work out. The function in this case can be anything. Can be a tree, can be a neural network, can be a set of basis functions. But the principle of amortization is more general than that. Again, you can use the same kind of principle for predictive distributions. If you're thinking about building Bayesian neural networks are different. You have data X, which you observed, and Y, which you've observed. And what is random are the parameters of that distribution. You typically need to compute some predictive probabilities. And the memoryless prediction basically asks you to do Monte Carlo integration. Again, the amortized inference is related to the idea of distillation, if that has come up during the week, of use a deep network, distill this Monte Carlo computation into a neural network. So you can do that as well. OK, so the last bit in this section I wanted to talk about was stochastic optimization. So this common gradient problem you have seen everywhere this week. It is compute the gradient with respect to some parameters of an expectation of a function. This is the problem of variational inference. It is the problem of the importance-weighted autoencoder. It is the same problem that you have in reinforcement learning. In variational inference, it's the log likelihood. In IWAys, it's also the log likelihood. In reinforcement learning, f is the return or the reward function. It's basically the same problem, and in other areas, this problem is one of the biggest problems you have in computational science. So there's sort of two terms. It's really difficult to compute this thing. A, you don't actually know this expectation. If you knew the expectation, then things were very simple. And B, the expectation is with respect to the gradient you want is with respect to these parameters phi, which live in the distribution you want to take the expectation with. So as I said, there are lots of problem areas. Generative models, as I'm describing, is one of them. Reinforcement learning that you saw yesterday is another one. Operations research and inventory control has this. Monte Carlo simulations of weather phenomena has this problem. If you want to do asset pricing and finance, then you will also see this problem. So it is really the same problem everywhere. So there are typically two approaches you can take. A deterministic approach, which means introducing some deterministic bound on f. And if the bound is deterministic and you can integrate each of these things, then the problem is very simple. In the 2000s, they would call these local variational methods. People don't like them as much anymore because finding good deterministic approximations can be quite hard. But the one that we prefer these days are stochastic methods. So they compute this expectation by Monte Carlo by exploiting properties of these distributions and these functions. Right? So there are two ways of doing this. You can either take the derivative of the function f, in which case we're going to call that the pathwise estimator, or you can take the derivative of the function q, in which case we're going to call that the score function estimator. And they have very different properties and different ways in which you can use them. So you've seen all of these yesterday, so I'll go through very quickly. The score function estimator says, I'm not going to make any assumptions about f. F can be non-differentiable, but q should be something that is easy to sample from. So what I can do is then transform this quantity into this new gradient estimator. It's actually a very simple gradient estimator. You saw it yesterday by using the likelihood ratio trick. This gradient is very interpretable. It's very intuitive, actually. It's a very randomized search. So what the gradient tells you to do is choose some z at random from everywhere that you see. And now I'm just going to evaluate how good this random z is. So I'm going to look what the cost of doing that z is. So take f of z and look how good it was. If it was good, f is going to be high. If that z was bad, f is going to be low. And then I'm going to say, well, just take the gradient with respect to that z and then reweight it by the cost. So it's a very randomized sort of search, but this is what you have to do if you don't want to make assumptions. And so you can see that the variance of these kind of estimators is going to be very high. Right? F of z is typically going to be a sum of k terms. And so the variance of this kind of estimator is going to scale linearly around order of k. But then you can do a lot of tricks to make this manageable. So it has many different names in the literature. The likelihood ratio methods is what you'll see in reinforcement learning. Reinforced and policy gradients. Automated inference is one. Black box inference is another method. The other way is instead to use properties of q and f directly. So f is now a differentiable function. If f is differentiable, then you can actually use a little bit more information. So I want you to recall those transformation models again, which was this piping system that we have that takes noise and gives you random variables. So if you have this, you can re-express this rather in the system of pipes. So saying z can be expressed in terms of a deterministic function z with some random noise epsilon. So then what you can do is wherever you see z in this expression, just replace it with g. Right? And this is the expression that you get. And it's very intuitive because all this expression tells you to do is just do backprop. Just take the gradient and push it all the way through all the functions that you have. And because of that reason, in an earlier paper, we thought to call this stochastic backpropagation. But it has many different names. If you look in this finance literature or stochastic optimization literature, they will typically call this perturbation analysis. The reparameterization trick, which Russ mentioned, affine independent inference methods. Right? So these are the two estimators that you get to choose from. There are other classes, at least two other classes of stochastic gradient estimators, but these two are the most general ones and the most useful ones for problems in machine learning. And so when you combine these kind of stochastic gradient estimators with estimators that use mini-batches, then you get what are called doubly stochastic estimation problems. Right? And you have to sort of control the noise. So great. I have half an hour left. Are there any questions on that section Yes?
So both the estimator are unbiased?
Yes, both estimators are unbiased in this case. It's actually very easy to see in both cases, because in the pathwise estimator, because you can undo, you get back the same integral that you had before, and in this case here, because you can always reweight, in both cases we actually use the property that they're unbiased to do that. You can create unbiased estimators, which also work, but you know, people don't like unbiased estimators. You need to know what Q is, and you need to exploit that knowledge. If you aren't willing to exploit that knowledge, then you can only use the other estimator, right? It's all again about knowing your problem and deciding what is best for your problem. Okay. So I wanted to use a case study of variational autoencoders, but this can be for any kind of generative models to explore different ways of building these kind of models and different assumptions that you can make. So as I said, a variational autoencoder is the principle of amortized inference applied to latent variable models. And this is the loss function that we have, which is this variational free energy. And we've already introduced that a way of dealing with this is by building a model and an inference network. Right? And there are many design choices that you have to make. You can decide what kind of latent variables you're going to use. Are they discrete? Are they continuous? Are they Gaussians? Are they Bernoullis? Are there some mixtures of things? This is something you have to decide. You have to choose what kind of model or likelihood function you have. Are you happy to deal with IID data? Is there some sequential aspect to this data? Are there temporal properties you need to model? Are there spatial properties? And all of this knowledge you need to build in. And then this inference network, you need to also decide some properties. What kind of distribution does it have? Can it be multimodal? Is it sequential? Does it have spatial properties? So all of these things you need to do. But the things you do not need to choose, because this is what we'll do for large-scale deep learning, is we'll always use stochastic gradient descent, and we'll always use stochastic gradient estimation, these two properties of inference that we just did. So I just wanted to make a quick mention about how you implement these things. These days we have many different tools which make implementation easier. So we have Theano and Torch and TensorFlow and Stan. All of them are easy, and if you're doing message passing, then infer.net is a good one. And so you have a forward pass, which is sort of as follows. You take data x, and you pass it through a box, which is some function, and out of this function needs to come a sample of the latent variable and the computation of the entropy. So this is basically the function that you need to compute, which we'll call the recognition model or the encoder. Then you need to implement two other things. You implement another box, which is the prior. Typically, the prior doesn't have any parameters, so it just needs to evaluate the log probability of a Gaussian. And then you need to implement one last function, which will be the model. And the model will actually put all this likelihood computation and structure in there. Yes?
In principle, you don't need to have an analytic expression for the entropy. You could also sample it if you have Q.
Yes, yeah. It can. How h of q gets computed can be by Monte Carlo, or if you know it, it can be done exactly. So, but once you put these things into a computational framework like Torch, or Theano, or TensorFlow, you immediately get back the backward graph, and the backward graph will then, when you go backwards, computes the gradient of the prior, gives you the inference. So all the pictures that I'm going to draw are drawn in boxes of these three types so that you see exactly how you implement it and what the flow of the gradient is like. Because the flow of the gradient depends on the type of estimator for the gradient that you use. Ideally, what you want is some kind of probabilistic programming that uses variational inference in this case, and I think we're very close to that given the tools that we have. Right, so the standard things are always the case. Stochastic gradient descent and precondition optimization you'll use, like RMS prop or ADAM. You implement your code on GPUs of some distributed clusters. And because these probabilistic models are modular, when you code it up, this prior itself can be an entire VAE. And so you can build VAE modules. You can use that in a prior of another VAE module. And you can make a very complicated code base this way. So OK, the simplest kind of VAE that you can deal with is sort of this latent Gaussian VAE. And the prior is just a Gaussian distribution. And so basically, you implement an evaluator of a Gaussian probability, which is easy to do. Then you have a model P of x given z, which is very simple. It says just give me the probability of x given some function of those latent variables. And the function, in the simplest case, be a Gaussian, but this can be any distribution, exponential family or otherwise. And it has some parameters, theta. And the recognition network is going to be equally simple. It's just going to give you a Gaussian with some nonlinear functions for mu and for sigma. And when you plug this into your automatic differentiator, you'll get the gradients of all of these things. The model and the inference can be fully connected, or it can be convolutional. This is easy to do. And so when you read in supervised learning all the latest advances they have in building models, when you see things like batch normalization, dilated convolutions, and skip recurrent connections, and whatever, you plug them into these models and you build better models that way. And so there is sort of this cycle of life which happens in machine learning through all parts, right? So all the functions are deep now. So these kind of latent Gaussian VAEs can do a lot of interesting things. So the first one I mentioned was about this visual concept learning. So they can disentangle input data in interesting ways. I showed you the video, it's not playing here, about how it learns to separate the fact that there's an oxygen bar from the motion of the submarine, which can go up or down. These latent variables can help you do visualization of very high dimensional data.
So can you explain how these images were obtained? Is it by moving in Z space?
Yes, so yeah, basically you take Z with 10 latent variables, you clamp 9 of them, and then you vary 1, and then you look to see exactly what happens, and then you see one of them deals with oxygen bar, another one is just with the motion up and down. And I think this is a nice property that you want out of systems that reason. Yes?
Sure. Well, how can it do it if it's a prior? It's a Gaussian, right? So you can arbitrarily rotate things around.
So yeah, so in that particular case, what you do is you introduce an additional penalty onto this KL constraint that reduces its contribution, and then what comes out is sort of these kind of contributions. But yeah, Gaussians. But once you have a fixed model, when the parameters are fixed, then this problem disappears, right? Because then for a fixed model, then permutations don't exist anymore. I mentioned visualization of very high dimensional data. And in this particular graph, what is very nice with these kind of models when you can actually evaluate the probability is that you can plot all your data and you can resize the shapes by the contribution of their marginal likelihood. So data points that have a great deal of contribution have very large shape, and things near the decision boundary have very small contribution to the probability. And in this video here, is sort of just exploring this dimensions of MNIST videos. Let me see if it plays. Yes?
I didn't quite understand your answer to Wes's question, because we know the VAE already does disentangling all on its own.
Yeah.
So that wasn't enough to do?
So for that, that's not enough. Because I don't know, these kind of games have a bit more other properties. They're very deterministic. So then you want to sort of emphasize the deterministic aspect more. So you downweight the scale term relative to the reconstruction term. And then you can sort of see these kind of structures come out.
So was that your answer to get the different dimensions to not be rotation invariant?
Yes. At least in this case, that's just one simple way of doing it. Otherwise, as you said, they can do them themselves. On faces data, you don't have to do anything special, right? Are there any other questions while we
I
are?
don't understand why playing with the strength of the KL term has anything to do with the rotation in Z space.
So what this happens, yeah, this is, I'll tell you, we could talk about this one afterwards, I think. It's a big debate. Anyway, so I wanted to mention VAE representation. So you can learn a latent variable model of these from a data set. This environment is called Labyrinth, and the task that you have to do is, it's called forage and avoid. You need to go and collect the green apples, and you need to avoid the lemons, right? And what you do is you learn a VAE, and these latent variables now form the representation. And you store these representations in what is called an episodic memory. An episodic memory is basically a k-nearest neighbor. And what gets stored in this k-nearest neighbor memory is the actual representation, the return that you got from that episode in the data, as well as the action that you took. And it always stores the best return. So this is a system of episodic control. And this is one way that generative models can help in the problem of control. Yes?
So in this case, one thing that the NRL people are grappling with is that if you just train good models that reproduce the dynamics of the environment is not enough. You really need to have good models where the reward is.
Yes.
So how does the reward come into play here as opposed to just the distribution of the data and the visual?
So the generative model is only used to give you the state representation, right? Once you have the state representation, that gets stored along with the reward. Not the reward, actually the return for that episode.
But the
right?
return doesn't inform the state representation at
the return does not inform the state representation in this case. It would be nice to have maybe something that does inform the state representation, but you also sort of an exploration to see how modular kind of system we can build in this case.
But in this particular case, the return is very tied to what the state representation ends up being anyway.
Yeah, yeah, because at least in this kind of simple or in that other maze navigation environment. Yeah.
In this case, if I just get random projections.
Random projections also work, they just don't work as well. They have an experiment that compares random projections versus VAE to look at exactly what other kind of sources you can do. But
in principle, you want to backpropagate through the state representation.
yeah, you want to have a model that's part of the learning system. And it's very difficult to differentiate through k-nearest neighbors, and so this is the problem. But because we're doing lots of research that you saw earlier in the week about memory systems, I think this will also get addressed very soon. Right? So this is the problem that we call episodic control, just to explore one way of using generative models for control problems. So one of the problems that comes up from these latent Gaussian models is that the real kind of posterior distributions that you see are very complicated. They have distributions that look like this, and if you use a Gaussian, that might be okay, but real distributions actually look more like this, or like this, or like this. The gray stuff is the true posterior in this case.
Sorry to derail.
Okay, good.
The last work, was it published?
Yes, everything here is published. I'll put the references. I just haven't had time, so. What was I saying? Power of good posteriors. Okay, so real posteriors look more like things like this. If you put a tan H in your model, all of a sudden there's a donut with a hole. And so really you need to build a Gaussian for a posterior distribution is not going to be enough. So we're going to have to do a lot of work in this domain. So we'll come back to that a little bit more. Let's replace the Gaussian and put a binary latent variable instead. And so same model, you implement a box that gives you an autoregressive Bernoulli distribution as one example. You build a model, maybe the output is also an autoregressive Bernoulli distribution, and then you build the same thing through an inference network that gives you binary data. Everything is binary in this case, very similar to a sigmoid belief network. This is called a deep autoregressive network. And again, you can derive the gradient estimator in this case by using the score function technique. And in fact, in that paper, there was a slightly biased estimator. But anyway, so this is some of the things that you can do with the earliest versions of this kind of model with binary latent variables. But I just wanted to point it out to show that if you are interested in having binary latent variables because they offer you interpretability in some way or other ways of disentangling your data, then that is possible to do. So these were on some binarized Atari games. The problem of semi-supervised variational autoencoders is another good one to look at. Here we can do a little bit more. We build a prior function, and we also include a prior over classes, which we'll assume is unobserved. These two things feed into the model. And then we build an inference network that gives you both the posterior distribution on latent variables as well as the posterior distribution on the class probabilities. And again, like we showed for the generative models, the progress in semi-supervised learning has really gone well. And the generative approach really is the state of the art for semi-supervised learning right now. And I think there'll be lots more work coming in this front. And they let you explore the data in various different ways. So the problem of these posteriors that I mentioned can be addressed by a different kind of way of building up your posterior. And this is a model that we call draw. So draw itself is very much like a latent Gaussian. It is a latent Gaussian VAE, but I'll call it a sequential latent Gaussian VAE. You have a prior box, and the prior itself will have a sequential structure. It will say form Zi given all Zs that have come before. And how this conditioning, I'm going to leave to a detail for the next slide. Then similarly, you can build a model which is going to form this distribution based on all the Zs that you have generated, and then the inference is also going to generate these Zs in a sequential fashion. So in more detail how we actually do that, you do this sequentially. You take time point 1, you generate some prior, and then you fuse this using some RNN and LSTM in this case. You do it again, generate a new source of randomness and fuse it this way. And eventually you can do this for as many steps as you like. And then you can generate the final state, and then you can generate your model and generate the data. And the inference is where this comes in. You can take your data X with some state and generate this Gaussian, and then you do the inference sequentially. And because of the conditioning of how the distributions Q of Z is related to Q of Zi in a very nonlinear way, the final distribution, which is the collection of all the Zs, is something multimodal, can be very complicated, and is actually the thing that will help you get very good results. So these state things can be LSTM or GRU units. If you want to include attention, like we heard this morning, through spatial transformers or hard or soft attention, then that's easy to do. Let's see, I wanted to show you. Yeah, you can have different LSTMs, or you can share them in this case, and you can even introduce additional canvases. So here's just 2 videos of it generating faces on the multiply data set with the attention window in this case. And then there's a different kind of model of it generating omniglot digits. And I just wanted to show this video to show how the drawing process changes depending on the type of LSTM that you actually use. So if you have this additive canvas, which is just adding things, then it's more drawing-like. But if you have the CGRU kind of canvas, it's more like a gas that is remolding itself and changing over time. But in the end, you get equally good generations. So the additive canvas is good enough. So if you wanted to build other kinds of even more structured and sequential VAEs, then here's a different model of the kind to do scene interpretation. So I'm going to structure my prior in such a case that it's going to tell me 3 things. It's going to have a prior over what is in the image, a prior of where those things are in the image, and a prior of whether this is the last, if I'm still counting, how many images there are, objects there are in the image. So I'm going to have a prior for as many objects as there are in the image, and then I'm going to fuse them together and generate the data, right? So the prior probability is P of what, P of where, and P of whether I should continue to generate a new object, and then the likelihood is that way. And then the inference is sequential as well. You take data through some LSTM or RNN, and you form an inference over what and where and whether to continue or not. And the point I wanted to mention about this model is that this is one of those models that combines binary and latent Bernoulli latent variables. So the binary or the continuous ones are the what and the where, and the discrete variable is this probability of continuing, which helps us count how many objects there are in the image. So in this video here, basically, it's a demo which is going online, and you get to draw MNIST digits in a little window. So when I draw 1, basically, the object knows that there's 1 object, and that's how to generate it. As soon as I draw 4, then it knows, oh, there's a new object. It knows that it's there, where it is in the image, and what it is. These are some limitations that you see of this kind of model. It was only trained on MNIST digits of a certain size, so a very long MNIST digit becomes 2 MNIST digits, and 8 gets recognized, but a very large 8 is seen as 2 zeros. So these are the kind of things of how your data is used affects your training. OK, you can extend all of this to be more than spatial, more than temporal. You can even do volumetric. So again, in the sequential VAE setup, generate all the priors, and you build your model based on volumetric data itself. And here, what I wanted to point out is that this kind of model now need not be a model that you learn through a ConvNet or volumetric convolution. The model itself can also be a graphics engine. And you can take derivatives through this graphics engine using that score function estimation technique. Right? And so you can use volumetric convolutions and volumetric canvas in this case. You can have 3D attention using 3-dimensional spatial transformers. The volume you can use this 3rd dimension to represent color channels or some volume in space, or it can even be time if you wanted to do that. And I mentioned the non-differentiable aspect. So here's some results on this volumetric VAEs of generating some 3D shapes from the ShapeNet data set, which does really well. And at least in this case, we can actually also produce a set of benchmark results using the likelihood function to actually test how well we'll do. And on this model here, we actually use a rendering engine as the generative model itself. And then we look at the kind of reconstructions that can happen, because what the model needs to do is learn a mesh representation internally that matches to the renderer. Yeah.
Is that the 3D rendering using like a 3D ConvNet structure? In
the top image, yes, it's using a 3-dimensional 3D convolution effectively. And in the bottom one, it's an OpenGL renderer in that case. OK, I think this is the last one. This is the model that we called straw. And this is the one where I wanted you to think a bit more about reinforcement learning again and how we can form temporally extended actions. So again, you're going to have a prior. And the prize is going to be split in two parts. We also saw something similar to this morning and yesterday. The prize is going to include a latent variable of Gaussians, and then it's going to include a set of actions, which is going to be conditioned on that set of latent variables. The actions are unobserved. They are also latent. So because they are latent, we're going to have to integrate them out later on. But you can implement these two boxes. The action is discrete. The prior is continuous. Then you have the model, but in reinforcement learning, if you want to be model-free, you won't have access to the model. You will use the environment, and this will just be the reward or the return directly. If you wanted to do model-based RL, then you can put some kind of another generative model to model the environment of the kind that I showed you earlier here. And then what you can get is the log probability of these returns. And then you need to do an inference of some sequential form of taking data, giving you inference of Z, giving Z, and then giving you the sequence of actions. And I'm not going to just generate one action at a time. I'm going to generate an action from now to t points in the future as well. And so this is how I'm going to do the temporally extended planning, right, by generating these kind of actions. And I'm sort of writing it this way because I wanted to introduce you a slightly different concept, which is the concept of the variational MDP. It's also very familiar, and the kind of loss function that you get out can be derived using the techniques of importance sampling that I showed you earlier. And yesterday, Peter mentioned a bit about these sort of entropy penalties that can be introduced, and you can see through the variational MDP framework how entropy penalties can be derived and other ways of deriving alternative kind of penalties. Right, so this kind of loss function lets you maximize the return, which is the value, subject to some KL constraints on a embedding space, but also ensure that you do some exploration. So this is a very nice principle for doing reinforcement learning. And so in this kind of model, we tried it out in Miss Pac-Man and a number of other games. So the number of actions, the main one is this action plan, which is the number of actions which is discrete. And then time is in this case. As I said, white is the current point in time. And if you look, there's always some gray parts in the future. White is sort of high probability of taking a particular action. And you can sort of, and then this value function at the bottom is what we use as the baseline. And it actually does pretty well. And it was a good way of exploring how generative models can be used, yes?
Why are you doing this open loop as opposed to closed loop?
Well, next round, I think, yeah. It was just the first setup to try it out and to see how these things combine together. But closed loop planning is the thing that we actually want to do. But then you have to build a more complicated feedback system. And if you look at, you have to do a lot of other things to actually make the optimization work. This kind of optimization requires you to use everything you know about stochastic gradient estimation. You have to apply the score function estimator here. You have to apply the pathwise derivative here and there. And so you have to do a lot of work to actually make the estimation work. So, but open loop, a closed loop would be the best way to do it. OK, so that was macro actions in learning. So let's summarize. I sort of wanted to demonstrate, I think I have 11 or 13, or I don't know, different ways of building generative models, this world of generative models, which I wanted to share the reason that I love working in this area with you. There are all these different ways of working in it, and we described 3 different kinds of generative models: fully observed models, transformation models, latent variable models. We looked at all the progress that has happened over many years to really improving these models and making them usable in different kinds of setups. We can look at the quality of the images that we have. There were 2 learning principles that we looked at: the principle of model evidence, if you are interested in knowing the marginal probabilities, or the principle of 2-sample testing when you aren't interested in that but still want to do some kind of probabilistic reasoning. We looked at amortized inference, the way of introducing inference networks, stochastic optimization, and different kinds of estimation procedures, different families of VAEs, and different assumptions that you might want to make. And yeah, then what is the future of generative models? And there's a lot. The first one will be to come to the aid of supervised learning and reward-based systems. There's a strong role to have calibration, confidence interval, more robustness, some sort of interpretability, to form more data-efficient learning systems, to help us be more semi-parametric, to combine non-parametric and parametric systems, to do this new age of scientific discovery, exploratory analysis, synthesis and simulation, and ultimately to build these kind of complementary learning systems that build rich scene understanding, are self-directed and curious agents, have conceptual reasoning, and integrate planning and control. So I have lots of people to thank you. Thank you for your attention.